Good day, folks. This is tutorial number 12 in a playlist that is called Dynamic Scenario Animation and Modeling in 3D Experiences platform. In this problem, I will be modeling a simple pendulum, which is supported by a spring, as you see here. I'll talk about talk about this thing in more detail as we go along. So this is actually made out of three parts. One of them is, of course, the fixed wall. To avoid making a lot of unnecessary features for a thing that's not moving, fixed wall, I just made it out of two pieces. One of them is where it's going to be holding the spring. The other one is going to be actually the pivot point at the top. Then we have a rod, which is going to be massless. Okay, so I will make sure that the mass of this rod is very small compared to the mass of the bulb, or this thing that's I call the mass. This is the dumbbell, which is essentially the mass which makes the pendulum to swing back and forth. And then there's a spring here. Okay. Uh, now, the stiffness of the spring is given as 10,000 Newton per meter, or equivalent to this unit. However, I want to point out that instead of making these parts, I have already done it. They're very simple parts, but I will provide you the dimensions of it at the very end of the slide presentation in case you want to create it yourself. So here's the situation. The equilibrium position of the pendulum is the vertical position, and that is why the reference length of the spring, and that means the unstretched position, unstretched length of the spring is 0.175 meter, okay? And it's located at 0.3 meter from the pivot point, and the length of the spring is 0.5. The mass of the dumbbell, or this mass, is going to be 44. Oops, this should be kilogram. Sorry, this should be kilogram. All right. All right. That should be kilogram. And the mass of the rod, whatever it happens to be, I will change it so that it will come out to be 0.5 kilogram. Because remember that when you do these problems in 3D Experience, you have to declare the weight, and I'm going to declare them based on the properties of steel. So once it does that, you create that, you can go and change that weight, okay? And the wall is not going to be moving, so for some reason it came out to be 2.032. My guess is that when I modeled this thing with steel, these two pieces, this one and the pin up there, is going to have some value 2.032. We'll find out. And it's irrelevant because that's not going to be moving. Now, this particular problem, uh, oh, by the way, here is the data that we're going to be using later on. Remember, I said that the mass is going to be 44.264. The the rod is going to be 0.5. I'm going to declare it to be 0.5, and the wall. I think this is going to be based on the properties of steel. I didn't change it because it's not moving. We'll find out. Now, uh, the damping, there is no damping here, so the stiffness of the spring is 10,000 kilogram per second per S2, which means that I have to make a correction in the unit that I put down in the presentation. I say kilogram underscore S, it should be underscore S2, which means kilogram per second squared, alternative Newton per meter. And the free reference length of the spring, I will declare it to be 0.175. Okay, there is no damping here. So I'll use the DASSL integrator. There's two integrators, DASSL, and the other one is symplectic Euler. So I'll use this over a 4-second interval. And this is a problem that you can find a solution of it to basic vibrations textbooks. So the formula for the frequency of the oscillation is going to be right here. And if you take 2 pi divided by omega n, you're going to get 0.611, the period of oscillation, and we're going to compare our results against this, okay? So these are the dimensions if in case you want to do it yourself. So just move on. The only correction that I have to make is this should be S2. Okay, fine. Now let's go ahead to 3D Experience. The parts are already made. Okay, there is a rod. This is the rod. The mass is this dumbbell, the orange one, and the wall is that yellow piece that you see here. So first of all, I'm going to fix the rod. I'm in assembly design, so I'm going to go to engineering connection, fix the wall. Okay, it's fixed. Then I'm going to create a revolute joint between this rod and the pin up there. So let me turn this thing around so that it's in the same orientation as we had before. So let's do two revolute joints. One of them is revolute. Okay, and there are different templates that you can use. I would like to use this one, although we don't have to control anything. There is no, the last one, the offset is not going to be used for us. So I'm going to use this template, axis, plane. Okay. So the axis of this pin and the axis of that hole. Let me see if I can find the axis of that hole. And then the vertical plane, for example, this vertical plane of the wall and this vertical plane of the pin. And this thing, I don't need it, so I'm going to delete it, and I say okay, and update. So there we are. So this is already mounted. Okay. Okay, now we're going to be assembling that mass, another revolute joint. So another revolute joint, same template between the axis of this hole and the axis of this dumbbell here, and the vertical plane, for example, of the we can use the rod, and the vertical plane of the mass, the appropriate vertical plane, which happens to be this. And I don't need to control this thing, so I'm going to uncheck that or delete it basically. So what's going to happen if you update, there's a situation. Okay, now I have created a point already on this side face, and a point there which I can show you. So for example, if you go to the mass, not the mass, sorry, the wall. If you go to the wall, for example, let's see, the wall on the part, there is a point that I have created and it's hiding right now. So if I show this thing, there's going to be a point right at the center of this wall. Hide and show, you can see that right there. And there is also a corresponding one on this vertical, on this slanted vertical plane, which is the rod. Where is the rod? Here's the rod. There'll be several of them. Let me see which one this. I think this one. Hide and show. Oh, not that one. I don't need that. That's unnecessary. Right there. Okay. So basically, these are created so that that distance is 0.3 from the center of this to that location on the rod is 0.3. All right. So go back there. Okay, so that takes care of this. We are pretty much done here uh, as far as the assembly constraints is concerned. Two revolutes and a fix. That's great. So now we're going to go to mechanical system design, because that's where we're going to create our spring and other things. Spring. Okay, so we can create the spring now and then do the mechanism representation. The only thing is that if you do it that way, you have to go here and make sure it's included. Or you can create the mechanism representation. Okay, right now there's going to be two revolutes and a fixed point right there. All right, so let's go and create create an axial spring. and the axial spring is between this point and that point. I'm not sure why it disappears when I do it like this, but I can go get it again from the wall, and it is this point on the wall, right there. You can see that, and the value of the damping. Click on f of x is going to be 10,000. Not the damping, the stiffness. There is no damping here. And for reference length, I put down 0.175, 0.175. Let me see for a second. 0.175 meter, very good. And then we say OK. All right, now, if you go to the mechanism manager, you see that the spring is not included because I did it after I created the mechanism. So you make sure it's included, say OK. And I'm going to move this thing. I'm going to move this thing so that it actually goes to the vertical position, equilibrium position. Okay. Just to show you that actually everything is working. So let's go ahead and uh, oh, material. Before I do that, well, actually we can do it now. So let's go to uh, uh, maybe the best way is to move and manipulate. And in order to get hold of that, the best way is to go to the uh, assembly. Let's go ahead here. Let's go to the assembly, and then I go and do a manipulate. Make sure all the constraints are respected. So check this box, and then you can, for example, rotate about an axis, and the axis that we're going to select is this axis. Okay, so look at what happened now. If I move this thing in there, oh, there, you see this? You see this? So it is working, okay? Revolute. This could have been also rigid if you wanted to, but that's okay. And that's okay. So we're going to say fine. The only thing is I'm going to move this thing to the vertical position. And the easiest way of doing this thing is either do that manually, or you can, if you want, you can just put a joint here and then make the angle 0 and then delete it. That's entirely up to you. Let me do this thing. Let me visually try to put it in the vertical position. The constraints are respected. I'm going to rotate about this axis. Okay. Whoa, 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 whoa. Almost vertical position. Okay, very good. And then fine. Oh, now remember that in order for us to be able to see the vibration of this thing, we have to move it off the vertical, because if it's at the vertical position, there is nothing for restoring force. So I'm going to move it, go back here, and remove this thing a little. Oh, yeah, cancel. I forgot to check that constraint box. This should be on. Rotate about. Okay, fine. So suppose that this is actually the position that we move. Remember, these are all small scale oscillation. So this angle cannot be extremely large. Maybe 10, 20 degrees is okay. But if you go 40 degrees, 50 degrees, this is all nonsense. Okay. So we say fine. All right, now we go back to the mechanism. But if double clicking here does not take you there, so what you can do is you can go just switch applications. Now you're there, and we have to define the properties, material properties. So here's the weight. Let me see now. These are all declared already because you already declared them. So if you click on this, if you click on that, let me show you. For example, look at the rod. Look at the rod. Right now, the declared weight is zero point 0.5. You know what? What I'm going to do is I'm going to say fine. I'm going to redo it. Okay. How about recycle this? Do this. Recycle. Okay. So that takes care of that. We'll fix it. Uh, right now it says 0. Okay. Let me try this one. I'm going to recycle it. Send it to recycle bin and select this one or this one. Send it to the recycle bin. Okay, let's do the top one. Send it to recycle bin as if we started fresh. Okay. So here's the situation. Notice that the 100% is missing. So I'm going to select that guy, rod, and click on the hyperlink. And right now they're all 0. So you select a checkbox here. So these are going to be the information based on the properties of steel. But this was a rod. I want this thing to be 0.5. So left double click on this thing and you put a 0.5 here. Okay, that's great. Let's do the other one. Let's do this one. Hyperlink. This one is the the dumbbell. First, let's declare it based on properties of steel, right there, 44. And I think that's what you want to keep, 44.25. That's okay. I don't want to change this thing. I'll just leave it the way it is. And then finally, I'll do the wall, click on the hyperlink, and click on properties of steel. And this is the mass based on the properties of steel. Since it's not moving, that's okay. There's no reason for me to change this thing. So these are the things that I already had from the beginning, but I wanted to show you how it works. Okay, good. Now, all right, we declared the weight, and now we're gonna go to mechanical systems experience. We say okay. Simulation is being created. Okay, so let's see what do we know. A gravity activate gravity excitation minus 9.8, excellent. And create a probe. And the probe, I'm going to select the point that I already created on this dumbbell. So if you go to the mass, the dumbbell, part, part body, I have already created a point there. If you say, how hide and show it, hide show. So it's going to be this point, okay? The probe is located at that point. And then we're going to go to dynamic scenario, send the excitation there, gravity excitation, send the probe there, and for duration, I just shoot 4 seconds. Okay, and this is the integrator that I was planning to use. And once you're done, you go here, right click, force the excitation. Okay, this is 4 seconds. Now we're going to plot the results. Plot the results. Let us look at, for example, deselect everything and look at the y coordinate of that point, and there we are. And if you look at it, the period is around 0.6 ish. Okay, you can do that. If you want to get a better reading, go with a table and find out when is it going to go to back to the same 0.83, 0.84. So you scroll down, 0.83, 0.84 is around 0.6, whatever, right there. Something like that, which is agreeing with the hand calculation formula, which is right there. All right, folks, so that takes care of this video. If you want to include damping, then you can do that. All you have to do is to go to for example, right here, go to the spring, double click on it, and then click on the damping and put the appropriate damping value that you want, which I'm not going to do that. Good luck.